I can start. Yeah, hello everyone. It's my pleasure to introduce our keynote speaker today, Professor Anne Collins. Anne received her PhD in cognitive science from UPMC. Then she was a postdoc at Brown University with Professor Michael Frank. And she's now an assistant professor in the Department of Psychology at the University of California, Berkeley. Also, I can say her research interest is computational modeling in human reinforcement learning and working memory. Today, she wants to talk more about the role of executive function in human reinforcement learning. Yeah, okay, and thank you for accepting the invitation. So please take it away.
And thank you so much for inviting me. It's a pleasure to be here. I wish I could visit Iran in person someday, but definitely not today. And I don't know how you guys do it usually, but I'm very happy to take questions as they go. Maybe Jamal, if you can flag me if I don't see a question in the chat or a raised hand, feel free to interrupt. Thank you. Okay, so today I'd like to tell you a little bit about some of the projects in my lab that we've done to show that executive functions contribute a lot to reinforcement learning. So reinforcement learning relies on multiple important variables, but in particular on two key variables that I'm going to talk about today. The reward outcomes that you get when you're learning, and your reward expectations, what you expect to get for any choice you make. And what I like to show today is that, and so basic reinforcement learning essentially combines those two quantities, compares the outcome you get with reward expectation, and uses this as a reward prediction error signal to teach, to learn those reward expectations over time. And what I'd like to show you today is that executive function contributes to both of those, to the brain processing both of those variables. Okay, so in the first part of the talk, I'll focus on the first idea. So reinforcement learning usually focuses on extrinsic rewards that are known to reinforce choices and recruit striatum. So here you have a baby that's discovered chocolate and discovered that it's delicious, and so is going to do again whatever it took to get chocolate. So that's the reinforcement power of primary reinforcers, sugar, water, etc. And we know that this activates the striatum in the brain, but we know also that more types of reinforcers exist. So for example, you can take a very abstract looking kind of visual stimulus like this that originally has absolutely no meaning to this baby, but over time comes to be linked with the possibility of buying chocolate or candy. So in that sense, it's a secondary reinforcer. And we know that the brain treats it in a very similar way to a primary reinforcer, also sees it, processes it in the striatum. And it can go as abstract as you want, essentially. So, you can tell the participant green circles are good, red circles are bad, and that's going to be same as winning or losing or something like that. Okay, so that's what people usually focus on when they do reinforcement learning, this kind of primary and secondary reinforcement. What I'd like to show you today is that we should really go further than this. So consider the situation of potentially extrinsically neutral outcomes that you might get. So if you're a scientist, you are probably often called to plot things like this. Variable A against variable B, it might look like a cloud of dots like this that has no correlation here. Okay, so this is extrinsically neutral. It's abstract. There's no values attached to it. But now if you had a goal in mind when you were plotting this, if you had a goal to show that variables A and B were independent, then this will feel like a win, whereas this other plot will feel like a loss, right? But now if your goal was to show that variable A is a predictor of variable B, the exact same outcomes are going to have the exact opposite role, right? So this is to illustrate that there are outcomes that are really extrinsically, as far as the world defines them, neutral, but in a goal-dependent manner, should be considered as having valence potential. And this is what I want to understand. When we have goals, how do we use those goals to translate outcomes into something that's like a reinforcer? It's I think, uniquely human ability. Animals can use, non-human animals can use abstract tokens as reinforcers, but these abstract tokens need to be trained to become such by consistently associating them with primary reinforcers. By contrast, you can you don't need extensive training for a human. A single instruction is sufficient. Okay, so the question we ask is, striatum responds to various types of reinforcers. What about this type of completely new goals, outcomes that are extrinsically neutrals, but might not be interpreted as neutral in a goal-dependent manner? And we have reason to think that the brain should treat those the same way, not least of which because of a large literature that shows that the reward network in the brain cares about many other signals than reinforcers. For example, it cares about information like reward or novelty, and a few other non-easily interpreted as primary or secondary reward kind of signals. Okay, so we're going to try to get at this from a framework of reinforcement learning. So we are in reinforcement learning, we assume that agents are in a state, use some kind of reinforcement learning algorithm to make a choice, obtain an outcome that then trains the reinforcement learning algorithm. And we're keeping it to the simplest possible reinforcement learning equation, which is this one, where the estimated value Q of a state and an action is updated in proportion to the reward prediction error here with a learning rate alpha. And so the question we ask is, how do we set this reward function for extrinsically neutral outcomes, but that might want to be interpreted as not so in a goal-dependent way? Okay, so that's the question we asked. Do single sub-goals reinforce our choices and recruit canonical reinforcement learning processes in the brain? So to ask this question, we developed a new experiment that's based on classic reinforcement learning experiments. So this is what a participant would see on the screen. So try to pretend you're a participant in this task to get a good feel of it. So they would first see a screen showing the condition of the current trial. So in this case, this is a classic reward condition. Participant has 1 or 0 points at stake in this trial. Then they pick between two bandits, two shapes, the triangle or the circle here. Here, the participant chose the triangle, and then they get feedback. In this case, they picked the triangle and they got rewarded. Okay, so that means that in the next trial, if they get to pick between the triangle and the circle again, they might pick the triangle again, might be rewarded again. There are multiple pairs of shapes randomly interleaved. So they might see another pair afterwards. Here they pick the cross, get rewarded again. And then they might go back to the triangle on the circle where they might pick the triangle again and not get rewarded this time. And the idea here is that the triangle is actually the better of the two, but the outcome is probabilistic. So maybe 80% of the time they'll get 1 versus 0 if they pick the triangle. Okay, so far, super classic probabilistic reinforcement learning task. Okay, randomly interleaved with those trials, we have another type of trials that looks like this. At the beginning of the trial, participants will see this, 2 fractals, one of which is arbitrarily labeled as a goal and the other arbitrarily labeled as a non-goal. Okay, so pretend you're a participant, try to encode this. Then participants get to pick between two different shapes. Those shapes never appear in the point condition. They only appear in the goal condition. So here the participant pick the diamond, and then they get an outcome. Okay, and now your job is to remember whether this was your goal or not. Okay, so in this case, it was your goal. So you pick the diamond, you got your goal. Next, you might start the trial again. And a crucial feature of this experiment is that you'll never see the same fractal again in a different trial. Okay, so at each trial, you need to re-encode a new goal and a new non-goal. Okay, so new fractals each time. So you need again to say like, okay, new fractal, this is my goal. Now you pick, the participant picks the diamond because last time it led to their goal. It leads to the goal again this time, but a different goal. And new trial, again, new set of fractals, pick the diamond again because it led to your goal twice, and this time it does not lead to your goal. So this is also probabilistic. Even though the diamond tends to lead to goals more often than not, occasionally it will lead to non-goals. Okay, so we have, so to summarize the experimental design, we have a pre-choice period in which we indicate the condition of the trial, then a choice period between two items, and then feedback. There's the familiar reward condition, and there's a single shot goal condition, where you have to, in a one-shot way, encode a goal or a non-goal as a good or not good outcome for this given trial. And this changes in every trial. The conditions are randomly interleaved. So there's one block in which you have randomly interleaved reward and single shot trials, but a given pair of shapes will only ever show up in one of the conditions. Okay, so there are 4 pairs of items, 2 of which lead to goals or non-goals, and 2 of which lead to 1 point or 0 point. And there's also crossed with this an easy and hard condition, which tells us how probabilistic the outcomes are. So 120 trials in a block, and then there's 2 completely independent blocks. Any questions on the experimental design before I move on to results? All good? Great, thank you. Yeah?
Sorry, could you explain again the experiment? I get confused a little bit.
Anything specific?
In the first time, goal and what is goal and no goal manipulation? I didn't get it.
So the participants are instructed to try to pick the shape that will lead to their goal. So in classic reinforcement learning experiments, participants are instructed to try to win points, right? So they'll learn to pick the circle here because the circle brings them points. Here, participants in this condition, in the goal condition, participants are instructed to pick the shape that is likely to lead to their goal, and their goal will be shown to them at every trial. Okay, because some of the shapes, for example, here the square leads to the goal image 90% of the time, but to the non-goal 10% of the time, participants need to learn to pick the square that will lead to that goal more often. And that's something that they need to learn by observing the outcomes they get. Does that clarify? Thank you.
Yes, thank you.
Hi, Anna. I also have a quick question. So what's the incentive for subjects to learn in the goal condition, goal, no-go condition? Do they are incentivized by monetary reward or? Okay.
No, they're not incentivized at all. Actually, we told them that we would track their points in the reward condition. And we give them feedback at the end on the points condition, but they have no incentive whatsoever in the goal condition. And that's on purpose because we want to take out any extrinsic valence out of the goal condition. That said, it's not possible to do that perfectly. You know, like there's plenty of extrinsic motivation that comes from making the experimenter happy or whatnot, like this kind of things. But hopefully those are equated across the two conditions. Thanks for the question. Any other questions before I move to the results? Great. Okay, so how do participants behave? So despite this lack of extrinsic motivation that was just pointed out, the first thing is that participants learn in both conditions. So they definitely learn to pick the better of the two options in the single shot goal condition. But you also see very clearly that there's two main effects, essentially. The main effect of difficulty on the performance. So people do better on the easier than harder condition, which makes a lot of sense. They also do better in the familiar reward condition than they do in the single shot condition. Okay, so familiar reward learning is slightly more robust, but participants do learn from those single shot goals too. So why the difference? Well, it's harder for sure. You have to hold in mind the goals as you're making your choice to be able to interpret the outcome. But we were wondering also if this would introduce some kind of dual task effect. And if so, we were expecting reaction times in the single shot condition to be slower. That's not the case at all. We have in reaction times, we have a main effect of difficulty, but no main effect of condition. So it looks like the choice process, as inferred by the reaction times, is not different between the two conditions. So for example, there's no simple dual task effect, or there's no specific planning happening, for example, in the single shot condition. Last, we also collected a measure of individual differences in working memory with an n-back task, and we found that n-back performance selectively predicted performance in a single shot condition compared to the classic reward condition. It looks like working memory selectively correlates with single shot learning. And we can control for difficulty or any ceiling effect here by restricting this analysis to the two middle bars here. So the hard familiar condition versus the easy single shot condition, because they have equivalent overall performance. Okay, so we show learning from goals that looks similar to learning from rewards, except that it's slightly less good, essentially, and it's seems to be more directly dependent on executive working memory. Okay, so we try to understand this better, and first we put this into a computational model. So we try to capture the dynamics of learning with a classic reinforcement learning model, where we track the value of each bandit, for example, the star, as a function of the reward prediction error. We tested a bunch of models to try to explain the difference between the conditions, making the parameters dependent on condition. And the winning model was a model in which the learning rate was different for the two conditions. So something of note is that we did have a model in which the choice was allowed to be differently noisy in the two conditions. And this model did not win at the group level. So again, showing that one-shot goal is not worse just because it's noisier kind of choice selection. Rather, it seems like participants really learn slower overall in the single shot condition, as shown by those significantly lower learning rates. Okay, so worse performance is instead captured by slow learning, which could be due to, for example, lapses in encoding the goals during the experiment. Okay, so the next question we ask is, okay, so now we have those behavioral markers, and we have the computational model, and we want to ask whether the brain treats those two conditions the same way. So we put participants in the scanner and in an fMRI experiment, and looked at what we found there. So I'll give you the highlights of this. And first we focused on the familiar, the pre-choice period here. We found, this is more like a sanity check, we found that in the single shot goal condition, there was stronger activation of the control network, working memory network here, lateral prefrontal cortex and parietal cortex, as well as some hippocampus, as well as visual cortex. And that's logical because this screen is much more visually complex than this one. Okay, so this is kind of a sanity check. We're engaging essentially working memory processes and visual processes here in the goal condition. Now, if we look at the outcome here, our period, we again reactivated lateral prefrontal cortex more in the goal condition compared to the reward condition, which was consistent with retrieving from working memory this encoding of the fractal as a goal versus not a goal. We did not see this activity as sustained during the choice period. So next, we wanted to ask what was happening in the brain's reinforcement learning circuit. So to do so, we used the familiar reward condition to identify regions of interest. So as a localizer, really for reinforcement learning. And we looked at regions that were sensitive to expected value, to the outcome, sorry, the valence outcome, good or not good, 1 point or 0 in the reward condition, and found activity in the striatum and the hippocampus, regions sensitive to the expected value of the choice, and we found classic medial prefrontal cortex areas, and then reward prediction errors also in striatum and 2 other regions of the brain. So again, those regions were identified based on the classic reward condition. And then we asked, once we look in those regions identified by the classic condition, do we see the same signals in the one-shot goal condition? And indeed, that's what we found. We found significant activation of outcomes. So this time it's goal versus not goal in the striatum and hippocampus, as identified by the reward prediction of expected value and of reward prediction error, with a non-significant result here for the striatum, but once we did a more advanced encoding analysis of reward prediction errors, we did find reward prediction error-like signals in the striatum too. Okay, so the conclusion of this analysis is that canonical reward and reinforcement learning regions of interest also encode the corresponding one-shot subgoal reinforcement learning signals. So this is a strong conclusion that tells us that essentially the brain seems to be treating those one-shot goals in the same way that it is classic extrinsic reward signals. We wanted to go further to understand how the brain would actually translate those goals into rewards. So to do so, we did functional connectivity analysis from pre-choice period to feedback period. So specifically, we asked if you look at activity in the prefrontal cortex at pre-choice, where you're encoding which of the 2 fractals is the goal versus not the goal, we predicted that a better encoding at pre-choice should lead to a better reward-like signal at feedback. Okay, so we asked, is the strength of the signal at pre-choice predictive of the strength of the signal in the striatum at feedback? And same in the hippocampus, where we also had encoding of valence. And that's what we found. We found significantly stronger connectivity in the goal compared to reward condition between those regions, both of them. And we found that the strength of this difference here was related to working memory individual differences, as well as individual differences in the difference in performance between the 2 conditions. Okay, so the idea here is that those functional correlations seem to tell us that essentially we use working memory as a way to prime the reward system in the brain to interpret those goal outcomes as rewards. So we went one step further. We know that these rewards are processed by dopaminergic signaling in the brain, who then sends that signal to the striatum. So we asked more directly, does this one-shot goal that we store in working memory actually directly talk to dopaminergic regions in the brain? Okay, so we took a functional an anatomical region of interest in the VTA here, and we did this connectivity analysis, and we did indeed find stronger prefrontal to VTA connectivity in the goal than the reward region, although this was not significantly related to individual differences in performance. We asked whether what the role of the hippocampus was, and in particular, we asked whether pattern similarity between pre-choice and outcome was predictive of learning differences, and that's what we found. So it seems like there was some reinstatement of the goal happening that also contributed to interpreting it as a reward outcome. Okay, so the takeaways of this part of the talk is that learning from one-shot sub-goals may rely on the control network in working memory, and that such learning appears to drive canonical reinforcement learning neural signatures rather than a separate network, for example, such as a goal-directed network, as you might have predicted. And that top-down cortical input may prep those reinforcement learning circuits in the brain to transform novel goals that are extrinsically non-rewarding into standard intrinsically rewarding outcomes. Okay, so that's the end of the first part. I hope I've convinced you of a role for executive function to in helping us interpret random outcomes as rewarding in a goal-dependent fashion. In the second part, I'd like to show that executive functions also contribute to reward expectations, but I'm happy to pause here and take questions if that makes more sense, or I'm happy to take questions later if that's better. Okay, so let me carry on. So in this part of the talk, I'd like to first establish that another role for working memory in learning, a very direct role for working memory in learning, and then show you that working memory additionally contributes to setting reward expectations for reinforcement learning computations. Okay, so I've done lots of research in my lab showing the importance of working memory for learning. So you can think of, we talk a lot about reinforcement learning and the circuits in the brain that contribute to reinforcement learning. Working memory holds information in a different way than reinforcement learning. It's a very fast way of storing information that can store detailed information and is very flexible, as opposed to reinforcement learning that stores a specific type of information, the integrated value of something, learns it in a fairly incremental way, and is not particularly flexible. The cost of all this is that working memory can only hold a little amount of information in mind, whereas reinforcement learning can hold a lot. Working memory is of short durability and is effortful, as opposed to temporal stability of reinforcement learning and effortlessness. Okay, so we have a clear trade-off here between two memory systems. And so it makes sense to think that we might want to try to use the best of both in conjunction to make learning more flexible and efficient. Okay, so I designed a task to try to show this joint contribution. So in this task, it's also a reinforcement learning task, but slightly different from the previous one. Participants see stimulus on the screen. So here, this is a pumpkin, for example. They make a choice by pressing one of three keys with one of three fingers. And at the beginning, they pick randomly because they have no information about which one is correct. So here, the participant picked the index finger. And then they get feedback that tells them whether their choice was correct for this item or not. And then they get a randomly selected other stimulus, and this iterates for a while so that they can use their feedback to learn by trial and error, for example, to press the index finger for the pumpkin in this case. That makes sense? The feedback in this case is deterministic So if the index finger is correct for the pumpkin, it will always lead to a correct outcome, and all the other choices will lead to incorrect outcomes. And this won't change in the block. Okay, so it's a simple, very simple in a sense task. So in this block, for example, participants might learn about the pumpkin and the green beans. So they would see the pumpkins and the green beans maybe 15 times each randomly interleaved, and they would get to learn over time which key to press for each of them. The key manipulation in this task is that there are multiple blocks. Each block is independent, so introduces a completely new set of stimuli. And this set of stimulus varies inside. So some blocks have set size 2. You learn about 2 stimulus associations, and some blocks have size 3, 4, 5, or 6, where you might have to learn up to 6 stimulus action associations. The number of actions is always 3, so there can be overlap in the correct actions. Okay, so that's the crucial manipulation in this task. And why is it a crucial manipulation? Well, this is a reinforcement learning task, so it tests the role of reinforcement learning in the usual way by seeing how reward history impacts how likely you are to pick a correct choice. But it also tests the role of working memory with a set size manipulation. By changing the number of stimulus action associations you have to learn about, you induce a load effect potentially, which should target working memory, and also potentially a decay effect because you see every item less frequently. So there's more time potentially to forget in between 2 trials in which you get to try the correct action for the mountain or something like that. Does that make sense? Okay. So this is the experimental design. And I want to plot the predictions of a classic reinforcement learning models on this. So here I'm plotting the proportion of correct choices as a function of how many times a given stimulus has been encountered. So this is the first time any stimulus has been encountered, second time, third time, etc. So it's not a trial number, it's the iteration for each stimulus. Okay, classic reinforcement learning models predict that you just learn to aggregate the outcomes you get for a given stimulus. And for that reason, it does not matter what's happening outside of that stimulus. So the set size does not matter whatsoever. Okay, so classic reinforcement learning models make the prediction that there should be no effect of set size in learning. That's obviously a terrible prediction, as anyone who has intuition in this kind of task will tell you. This is what participants' learning curves look like in general. This is something that I've replicated like at least 10 times at this point. It always looks like this. In small set sizes, for example, when you're learning just 2 stimulus action associations, learning looks essentially perfect. So remember, there are 3 actions. So you try one the first time, you try another one, you try the third one, and by the third time you should have it right because there's only 3 options, and so you are at the asymptotic performance. Okay, so low set size looks like perfect memory kind of performance, but the higher the set size, the more incremental learning starts to look. Okay, so there's a very strong effect of set size. Here you don't see the error bars because they're so small. Okay, so this effect of set size on learning can't be accounted for by classic reinforcement learning. You can try to add whatever mechanism you want to reinforcement learning to try to make it look like this. There's ways to induce small set size effects. So for example, you could put decay into a reinforcement learning process that would create a small set size effect, but nothing that looks like what participants have. You could add interference, you could add your favorite mechanism to it. It just doesn't work. At this point, I've had so many papers reviewed and so many suggestions that I feel like I've tried everything. So instead, what we think is happening here is that to explain this pattern of behavior, you really need to consider this as the outcome of 2 processes contributing to learning in parallel. One of them is reinforcement learning. So with the same notations as before, you're tracking the expected value of a stimulus and an action, and you use reward prediction errors to do so. but the other one is working memory. And we have those two processes, and we assume that choice is a mixture of those two processes. So the probability of selecting an action is going to be this mixture between the policy from the working memory module and the policy from the reinforcement learning module. Okay, so again, the reinforcement learning module is classic. What about the working memory module? And what about the mixture weight? So we make a very simple approximation of working memory in this case, using kind of the classic and debated idea of a fixed capacity in working memory. So the idea that maybe you have 3 slots in which you can hold information. So you might remember the correct actions for the mountain, the lake, and the desert, but maybe not for those 3 others. Okay, we do this in a probabilistic manner. So we say that the probability of an item being stored in working memory is going to depend on the capacity. So it's going to be maximum for the number of items below capacity. But then anything over capacity, it's going to be in proportion to how many of those can be stored. So 3 out of 4 here, 3 out of 5 here, and 3 out of 6 here. Okay, so this is going to decrease as an inverse function of set size after capacity. Okay, so we have 2 important parameters here, the capacity and the actual maximum involvement of working memory in the policy. Okay, so this defines the mixture weight as the maximum times this inverse function up to a maximum. Okay, so that tells us the mixture weight. And then the actual working memory policy we encode as just being perfect memory of the last trial, but then decay at each trial for each information in working memory. So this is also an important parameter here, the forgetting. Okay, and if you want the specific equations, they're in all my papers, so you can take a look. Okay, so when we do that and fit the model to participants' behavior, we actually capture behavior much better than we do with any process that assumes just a single process. So that confirms the important role of working memory in reinforcement learning. So we wanted to confirm that this process we identify through behavior and modeling does correspond to a different process in the brain. So to do so, we did an Eeg experiment. This is me with an Eeg cap here, where we measure with scalp electrodes electrical activity in the brain. So we replicated the overall behavior. And then we first looked at stimulus-locked event-related potentials on correct trials as a function of set size. So the overall voltage at different electrodes as a function of time from stimulus onset here. And this is really just a sanity check. It's showing us that, for example, in this frontal electrode, there's a very clear effect of set size. So there's a signal to be picked up, essentially, that relates to this load, to this working memory. But it's also very unsatisfactory because there's plenty of things that are different between those set sizes, not just the set size, but also reaction times, expected reward, and many others. So there's confounding variables here. So we wanted to analyze this a bit more carefully to try to identify dissociable working memory and reinforcement learning components. So to do so, we did a single trial analysis of EEG voltage. So this is an ERP, the average voltage at the frontal electrode, for example. And this is the same signal, but plotted for each single trial, correct trial of a given participant. Okay, so this is kind of as close to raw data as you get. It's been cleaned a little bit, but otherwise it's raw EEG data from stimulus onset in milliseconds here. And you see that the signal is fairly clean, essentially. You can see the shape of the ARP. The color here codes the actual value of the voltage. Okay, and we want to say, see if in this signal we can find markers of reinforcement learning or working memory. It looks like there's a question.
Yes. Hi, Anna. I have a question. Why you consider FCZ and F4 in your ERP and single trial EEG analysis? Thank you.
Yeah, no, I don't. This is just for illustration purposes. You'll see later on that I'll show you a whole brain, well, whole scalp maps.
Okay, thank you.
Yeah, really just illustration purposes here. Okay, so we want to know if we can find error-like signals, like expected value or reward prediction error in these voltage signal across trials, or effects of working memory that should be, for example, set size or delay. So to do so, we just do a simple regression analysis. Essentially, we take at a specific time point post-feedback onset the variability across trials here for an electrode and a time point. And we try to see if we can explain it as a regression as a function of those various predictors. Same way as people do all the time in fMRI, but it is not done as frequently in EEG. And then we get those regression weights for each time point and electrode and participant, and we can analyze this across subjects as a function of time and scalp location. So when we did that, we find evidence for reinforcement learning processes post-stimulus onset very early on. So around 300 milliseconds, there's a very strong effect of expected value in a broad pattern across the scalp, but no effect of working memory processes early on, no effect of set size. Whereas slightly later in the trial, we find an effect of set size, but no more effect of Q value. And you can visualize this as corrected ARPs if you're interested. So this confirms to us essentially that we identify the two processes that we identified through behavior and modeling seem to relate to what we would expect in the brain, like a fast reinforcement learning-like process that occurs early on, but then a slower, more effortful working memory process. Okay, so we're going to use those signals here as markers for those two processes and see if we can ask more questions using those signals. In particular, one question we had was whether it's fair to treat those two processes as being independent. So far, the model just assumes that working memory does its own little thing, RL does its own little thing, and then the only place they come together is as a mixture for the choice process. But as you've already seen in the first part of my talk, there's good evidence for thinking that working memory actually contributes to reinforcement learning in a sense. So we wanted to ask this question here too, like, does working memory also somehow influence reinforcement learning at all? And we can ask that question by looking at those brain signals we've identified and saying if they are independent or not. So if reinforcement learning and working memory are independent, we should expect the brain's RL signals to be independent of set size. As a reminder, that's the modeling prediction. So we take the signal we identified here, and instead of plotting it average like this, we plot it per set size. Okay, and by the way, we identify a similar signal at feedback, not just stimulus lot. Okay, so what does it look like? So here I'm plotting this activity that relates to reinforcement learning here as a function of set size and also as a function of reward history. So the number of times that participants chose correctly in the past for a given stimulus. So this looks like a learning curve, and that's normal because that's how the signal was selected. So the fact that it increases is the definition of the signal. But what's not the definition of the signal is this set size effect. You see that the signal increases less quickly in low set sizes than it does in high set sizes. Okay, so that's a bit surprising because in the behavior it's the opposite, right? The performance increases faster for low set sizes than high set sizes, and so the reinforcement learning value should also increase faster. Okay, so we try to understand this as so this is the first marker of interaction between the two processes. And we first interpreted it as saying, well, maybe in low set sizes, because you're working using working memory well, you don't need reinforcement learning. So maybe you block reinforcement learning. So in modeling terms, that would be, for example, turning off the learning rate here, making the learning rate be 0. So that leads to a different prediction. First, if you simulate this, you do see this. Indeed, you see like lower increase in expected value for low set sizes, but you also see slower decrease in reward prediction errors, just because you're learning less quickly. Okay, so remember, we also have a brain signal for the reward prediction error, so we can test this prediction. And we actually don't find this prediction, we find the exact opposite. We find faster decrease of reward prediction error signals in low set sizes compared to high set sizes. Okay, so this interpretation is wrong. So what's happening? We thought that instead, what this is showing is that reinforcement learning might integrate working memory information. So how would that work? Well, imagine that you're holding in working memory the association. So you're holding in mind that you should press the index finger for the pumpkin. This also means that you should hold in mind, be able to translate this into saying, I'm expecting to get reward if I press the index finger for the pumpkin. Okay, so now the reinforcement learning signal updates its value using reward prediction error, and the reward prediction error is the difference between the reward and the expected reward. And this expected reward usually comes from the RL estimation. What we are saying here is that maybe this expected reward comes not just from what RL knows, but also from what working memory knows. Okay, so if working memory knows to expect reward, then maybe we can integrate this in the reward prediction error. And if we do that, then we replicate this, because in low set sizes, working memory knows a lot, and in particular knows to expect reward. So the prediction error is going to drop faster. But because the RL system hasn't learned this, it's not getting all the reward prediction error it should have to update its value. And so it's going to learn overall slower. So in effect, that means that working memory is going to block reinforcement learning from learning by providing information it already has. Okay, and that's what's consistent with the EEG data we have here. This additionally makes a prediction in terms of behavior that long-term associations are going to be learned better under the more difficult high set size condition than low set size, because reinforcement learning will not have accumulated associations in the same way. Okay, so we test this in a follow-up experiment where participants do the same thing as before. They learn stimulus action associations under different set sizes, where we predict that we should get better performance in low than high set sizes, because you can use working memory efficiently here. But then later on, we test the retention of those learned associations. So we take all stimuli from all blocks, randomly interleave them, and ask people to press the correct action for them and don't give them any feedback, so that they can't learn anymore in this testing phase. And here we predict that if working memory has blunted learning in low set sizes, now the retention in set size 3 should be worse than in set size 6. Does that make sense? So we tested this with just set size 3 and 6, and in learning, we replicate our usual finding that set size 3 learns faster than set size 6 with a better performance. And then we found in testing this very strong interaction where the drop in performance between learning and testing in set size 3 was much bigger than it was in set size 6. So there was a much bigger loss in retention there. Okay, so it looks like the brain's reinforcement learning computations don't operate in closed loop. Instead, it looks like working memory interferes in those computations in a way that it provides its expectations to it, which seems like a nice thing to do, except it's blocking the learning in this case. And so it's making RL learning slower. Okay, so to conclude, I hope I've convinced you that learning is a mixture of multiple neurocognitive processes that implement different computational trade-offs and rely on different neural mechanisms. That working memory interferes in reinforcement learning computations of value, such that what's learned faster is actually learned worse in the long term. But this interaction comes from some kind of shared cooperative information sharing. And also that working memory provides not just this kind of expectations, but also information about how to interpret goals as reward signals and expectations. So again, two ways of showing that the reinforcement learning processes in the brain are not at all this closed loop process as we think, but rather that executive functions inject information at multiple places of this computation, whether that's reward, expectation, or actually the rest of my lab also shows this at the state and action level. Okay, so that's, before I wrap up, I want to, do I have a couple minutes, Jamal?
Yeah, I think you have another 7 minutes.
Oh, that's great. Okay, so I think this is all theoretically very interesting, but I think I do want to spend a few minutes saying why this has broader implications, and in particular broader implications for individual differences studies, such as study of the child development or neurological and psychiatric diseases. Indeed, so we see lots of deficits or differences in learning behavior in many patient populations. And something to keep in mind is that we tend to model those with reinforcement learning, but they may not be attributable to reinforcement learning computations per se. Instead, they might originate in deficits or differences in executive functions and their contributions to learning. So I'll give you two examples from my lab, one in schizophrenia and one in development. So we compared controls, healthy controls, and patients with schizophrenia. These are the healthy controls. As you see, it replicates the findings from before, very strong effect of set size on learning. And then we asked how patients with schizophrenia compared. So here you see patients, 49 patients, and you see that they learn the task well. They show the normal markers of both working memory and reinforcement learning. So they have a strong set size effect, but they learn in all set sizes. But they perform worse than controls overall in all set sizes. Okay, and if you stop there, you have no way of knowing where this difference in performance comes from, what the process is that is impaired here. So we fit this model to participants' data, and then we can interrogate which parameters are different between the groups to explain this difference. And what we found was that participants with schizophrenia were fit with a significantly lower working memory capacity parameter, but no differences in reinforcement learning rate. And this was confirmed by showing that their test phase performance was absolutely the same as healthy controls performance. So their retention of information in the long term was the same as predicted, because you're using only reinforcement learning in this case, and there's no difference in the reinforcement learning rates. Oops, sorry. What did I do? Are you guys seeing subtitles too, or I think I subtitles. Okay, great. Okay, so this shows that the learning here is impaired in patients compared to controls in a reinforcement learning task, but this does not stem from their reinforcement learning processes. Instead, it stems from their weaker working memory contributions to learning in this case. Something we wouldn't have been able to parse out if we hadn't had this careful disentanglement of working memory and reinforcement learning. We did something similar to study adolescents. So we had a very large sample of a developmental sample, 8 to 18-year-old kids and adults. We tested them only in set size 2 through 5 for developmental study constraints. And what we found was a similar set size effect. So here I'm just showing you set size 2 and 5. And you see that set size 5 performance is lower than set size 2. And that adults and teenagers are indistinguishable from each other. The learning rates curves are really overlapping here, but that kids learn slightly slower than teenagers. Okay, and you can plot this more as individual performance. So here it's the overall performance in the whole task as a function of age. You see a very clear effect of age on performance, where the teenagers are similar to the adults. In this plot, I'm missing the 18 to 25 years old. We did fill that gap, and it's right where it should be here. We can also plot the effect of set size, just the slope of performance as a function of set size. And you see that this effect of set size decreases with age, but remains positive and at an adult level in the teenagers. But again, these descriptive measures don't tell you where the change comes from here with development. And so again, we fit the model and ask which parameters change with age to explain this change. And we had expected working memory contributions to change with age more than reinforcement learning contributions based on prominent models stating that prefrontal cortex develops later than other brain regions, essentially. And we didn't find that. We found no effect on working memory capacity or very, very weak effects on other working memory parameters in the brain. And instead, we found a very, very strong effect on the reinforcement learning rate that increased with age. So this was surprising to us, but I think is consistent with the rest of my talk that says that essentially reinforcement learning processes don't operate in a vacuum and instead take lots of inputs from executive functions. And so potentially what we're picking up on here is this input from other executive function that is increasing with age. Okay, so to conclude, I'd like to thank everybody who contributed to this research, in particular Sam McDougall, who was a postdoc in the lab and is now a PI at Yale, and did the first, the fMRI experiment at the beginning, and the giant team who contributed to the developmental research, including Maria Eckstein here, and the rest of my lab. And thank you all for your attention, and I'm happy to take questions.
Thank you, Anne, for your nice presentation. Everyone, any questions? Yeah, Sadep.
Hi, Anna. Thank you for great representation. A great presentation. It was awesome. I have some question. Can cognitive control and performance monitoring system communication be predictor of accuracy in RL task?
I haven't tested that directly. You mean the last task, the working memory and reinforcement learning task?
No. In general, in RL based task.
Are reinforcement learning based tasks predictive of what then?
No. Can cognitive control and performance monitoring system communication be predictor of accuracy in RL-based task?
Yes, I think they can be. I think I showed you an example at the very beginning, for example, of one measure of executive function. People might, disagree on, like, executive function is broad, right? So it's hard to know exactly which one, but there's definitely links between them. But I think RL tasks are very broad and recruit very different processes and different types of tasks, which is somewhat what I've tried to show here. And so I think it will often be the case, because I think executive functions often contribute to reinforcement learning, but maybe not always. I'm trying to make a point that reinforcement learning tasks are a much less unified family of tasks than they look like from the outside. We tend to model them the same way, but I think, you know, some of them might recruit more working memory, some of them might recruit more value-based processes and many other processes potentially.
Thank you. My other question is about what is effective more in our learning, stimulus encoding or feedback processing?
I think they're both very important. So I really focused on feedback processing here and expectation, but I also have work showing how stimulus encoding is crucial, actually. So if you take some of those tasks and modify the type of stimuli that people encounter, it has a very big impact on how their behavior looks. So I don't know that I can give you an answer as to what's more or less important, because that, you know, would be like, it's kind of comparing apples and oranges, but they're definitely both very important.
Thank you. And my other question is why learning rate in schizophrenia is more than a healthy subject in your task?
No, it's the same. It's the same, the learning rate. Let me just show you the plot again here. So you see that the learning rate is not significantly different between the two groups. And indeed the actual behavior that's measured in a way that should be only RL looks exactly the same between the controls and the patients. Mm-hmm. What's different between the two groups is the working memory. So it seems like the working memory is impaired.
Mm-hmm. Thank you. My other question is, are you consider separate learning rate in your models?
Separate learning rates for what?
In your model, separate learning rate, for example, negative learning rate or positive learning rate.
Yeah, absolutely.
For different type of feedback.
Yeah. So I didn't give that information, but yes, we have positive and negative learning rates. It's actually pretty essential in this task. Participants tend to have much lower negative learning rate and positive learning rate in this specific task. So yes, we have that feature in there.
Oh, and how to determine sign of learning rate, by prediction or error or by feedback?
That's a great question, and this experiment can't make a difference. It can't disentangle those two questions, because the feedback is deterministic. You know, a feedback of 0 is always a negative prediction error, and a feedback of 1 is always a positive prediction error. So it's completely confounded in our case. So we haven't tried to pull it apart. There's a recent paper that I've seen that looks at that. I don't remember what that conclusion is, but yeah. So I can't answer for myself.
Thank you.
You're welcome. Thanks for the questions.
Any other questions? Yeah, Amir.
Thank you very much for your nice presentation. I have 2 questions. The first question is for your first experiment. In this classical condition, the pre-cues have values, but in the fractal cues, they do not have any values for the participant. And I don't know how we can compare these two types cues when one of them has objective values for the participant and one does not have objective value.
Yeah, I totally agree. I think it was not a given that it should be comparable, which is why I think the result is striking, but in the end, the brain seems to treat them the same way. You're completely right? Like a priori, there's no extrinsic value in the goal condition, in the goal, fractals, and there is intrinsic, or at least learned, value in the points. And so that's why I think this finding is very interesting, because it shows that just by labeling this as a goal and a non-goal, immediately the brain is capable of interpreting this as having value. And that's what I find fascinating, because it's essentially enabling our brain to use this very old process, of value processing for something that's much more complex cognitively, just saying like, this is your goal, this is not your goal, go learn from this, right? So exactly your point.
Thank you. And for my next question is that, can we expect by changing the stimulus types in the working memory task, for example, putting some social stimulus in the first of block, and then ask to remember the social stimulus. Can we expect some effects on the learning rates, for example, in some sort of disorders like ASD or ADHD?
Yeah, that's possible. So I only showed you a few of the stimuli. Stimulus set, we have up to 20 blocks, so we have 20 sets of stimuli. So we had to go broad. So some of them have this kind of social flavor and some of them don't. And looking just at typical healthy population, we haven't found anything systematic about, some stimuli being easier to learn than others, within this range of stimuli where we've made an effort for them to be somewhat equally difficult, at least. So I think it's possible. I haven't done the experiment, but I've done a similar experiment. So essentially, I think your idea is that someone with ASD might have a harder time discriminating some social stimuli, for example, faces or something like that, which might lead to consequences on learning, right? So I haven't done that experiment, but I've done the experiment in healthy controls where I've made the stimuli more or less discriminable. So we've taken the classic stimuli, we've taken some blocks where we've replaced them with words that correspond to those stimuli. So instead of seeing an image of a pumpkin and an image of green beans, you would see a word that says pumpkin, a word that says green beans. And we've taken a third condition in which we've made it hard to discriminate verbally. So where, for example, the 6 stimuli might all be pumpkins, but different pumpkins or something like that. Okay, so we've done this experiment, and any of those 2 new conditions, impaired learning, and in particular the one where it's hard to name things, impairs learning most. But surprisingly, it impairs learning most in high set sizes and not in low set sizes. And when you do the modeling, again, contrary to our expectation, it doesn't impair working memory component of learning. It impairs the reinforcement learning component of learning, which I interpret in the same way as the developmental finding, which might, again, show this importance of the encoding of the stimuli, which might be dependent on executive functions as an input to the reinforcement learning system. Sorry, that was a bit roundabout, but
yeah, I understand. Thank you very much for your nice presentation again and your complete answer.
Thank you.
Okay, and I think we have 2 more questions from Sadr in the chat. Please have a look in the chat.
Great. Is this field mature enough for practical use in therapy, and how to get thought-provoking and practical question in this field? The answer to one is no, I think. I don't think this field is mature enough for practical use in therapy. I think, you know, I think we are, it's really interesting actually, because we know a lot, to the point that, for example, the NIH, the main funding agency in the US for science, is, you know, telling us to stop doing reinforcement learning because we know everything about reinforcement learning. But I think that's completely wrong, as proven here. It's like, you know, we really don't know how reinforcement learning interacts with other things. We really don't know how well it integrates other signals. So I think it's pretty far from, you know, us being able to use it in practice. I don't think it limits the, I think it's still fine to try to, you know, to try to go in that direction, to try to learn things, you know, as it relates to patients and to try things out, to try to learn. But I think we really shouldn't oversell right now the immediate usability and the likelihood that it will improve patients' lives very soon. As to the second question, how to get thought-provoking and practical questions in this field. By this field, do you mean reinforcement learning, or do you mean computational psychiatry, or maybe if you clarify, I'll jump to the third question. So the third question is, if you could adjust the function of the brain in such a way that our performance be better in feedback learning tasks, which area was your choice? Yeah, that's a tough question too, because essentially I don't think any region, I think this is all trade-offs, essentially. So I think, you know, and I think that the last experiment really illustrates this well. So this finding, right, where essentially by using more working memory in set size 3, you get to learn faster, but you get to remember less well, right? And this is a trade-off, right? That you have to make. It's saying like, okay, I'm going to use working memory, and that's going to make me more flexible and faster at learning in a dynamic environment, which is good in a dynamic environment, but which is bad if the goal is to remember things in the longer term. So I don't think there's a way to turn a knob that will have only positive effects, essentially. I think it will have positive effects in a subset of situations that will trade off with negative effects in another subset of situations. Probably not the answer you wanted. Sorry.
Thank you.
Okay, and thank you again for the presentation. It was our pleasure to have you in this mathematical psychology school.
Thank you. I was very happy to be here, and thank you for all the questions.
Thank you. Bye.
Have a good night. Bye.